onto the first talk of the day, and talk is called From Clutter to Clusters, and we will be speaking about logs, yeah, and usually been through this experience of, scrolling around the log file looking for what could potentially go wrong and cutting through all of the noise, until you found what you're looking for. And this is because the logs are the most prevalent signal how we kind of symbolize what application is doing. And that's because they are probably the oldest tool available to application developers and to the server developers. So we end up having high volume of those logs that are still usually just single message, that they are uncorrelated, and you really need to go into really deep investigation, especially when you've got like asynchronous process involved, that you don't know like to which particular object a log is related to. Yeah, like a typical example would be an exception that says incorrect order data with no further information. Yeah, so it's really hard to find out what is in there. They're also unstructured, so it ends up being a text file, which if you're looking for some particular point, it becomes hard to parse. Yeah, you need to do like a lot of regular expressions through to kind of make your query. On the other hand, it has a really interesting point to say. So if you then turn this logs into JSON, which I will recommend anyway, it will become much harder to read for humans. So then you really have to have tooling to understand what is there in the log files. So yeah, ultimately they're hard for humans to analyze. They're also freeform. So the text of the message is ultimately what the developer thought at the time of writing the code. That's what will be important for you. I remember planting that kind of time bomb for myself by seeing an error message in the log saying, "I told you so." Because at that time I exactly knew what that meant, but 3 months later, not so much. And they have varying importance. You've got things that happen regularly but are really just noise if everything works all right. And then things that are very rare but very important for finding out later bugs. So ultimately, we can say that logs are cluttered. And what I will try to show here is how to make sense of the logs, so that we can get an overview what an application is doing. So since we are collecting logs from multiple sources, multiple instances, getting an overview of what the system is doing. And the way we will do that is by grouping similar entries, and kind of the goal is to create a report that will give you a good insight of what might be happening with your system. And then you can act on that report to fix things. I don't have any specific tool to present to you, so rather I will be showing just the general approach, how you can do it, because in my experience, every system is different. So you will need to find out like your own way of viewing that. But it's not hard, and it is fun. If programming is fun for you, of course. Since I'm a Java developer, I will be focusing on Java application logs, and the code, the small snippets of the code I will be showing will be Java, and we will compare two approaches. One will use term vectors. So this is the concept from full text search, from information retrieval, and embedding vectors, which is concept from language models. If you've got questions, please head over to Slido, and we will be addressing your question later. So about me, I'm doing Java backend development since early 20,000s on various platforms, and I'm developer of Java backends since 2019. What I mean, I work with Paera. We develop an application server. I personally work on Pirate Cloud, which is a managed Java runtime when you drop a WAR file into the UI or over an API, and we make it work. We make it run on a Kubernetes cluster. No cloud setup, permission setup necessary. I'm also involved in microprofile telemetry, which is a standard API, not much of an API, just a consensus of how should Java runtimes handle open telemetry. Right, how did I come to this idea? So originally, a long time ago, we were migrating an application server. It was an SAP application server from one old version to one slightly less old version. And there were lots of business applications, and they were using the original logging API. That's also one of the reasons why the logs are so prevalent. We had API to do logs since forever, and that API is system.println and print stack trace. So it was really hard to make out like which application is making which log statements. So then the task was to collect all the logs and then group them basically by stack trace, so we can kind of assign exceptions to the application, and that we can figure out how much each application is logging and what could be the errors we need to fix before we do the migration. Then when sometime later when I joined Payara, Jakarta EE, TCK was open source, and it is a really huge test use. It has like almost 50,000 test assertions. The runtime for that is over 100 hours, and it doesn't tell you much about what went wrong. It will list you the test cases that failed. So in order to find out what happened, we had to look in the output from the test runner, which wasn't JUnit, by the way. It's something much older. And then look on the standard output of the console, and then most commonly the real cause or the error will be in the server log. So it was again the same exercise: collect everything, then kind of partition the logs by the time window during which the test was running, and then again group the contents to find out like what is the possible cause. The scroll you see at the beginning was one of the server log files, which ended up with a class exception. And ultimately we will find out, all right, so this class file problem is causing like, I don't know, 4,000 test failures. So once we fix that, we probably fix the largest problem, and then we can focus on the smaller ones. And since we launched Pirate Cloud, which is a distributed system, and I was thinking, all right, what is happening? We've got our QA, we've got our integration tests. Still, production is a different world. So we set up a regular process. Yes, so we collect the log files, run it through such a pipeline, and then we decide to fix bugs or to reuse Clutter, so to have less noise in the log files. Okay, so how do we go about that? So you'll need to build a pipeline that consists of these steps. Where first, your aim will be to get all the relevant log files into centralized location, ideally to a local computer, or have a query that allows you to extract lots of them. Then you will need to parse it. So find out like what is the body of the message. At the very least, just being able to tell individual messages apart. And then we'll do vectorization. So we turn the text into some numerical representation, because numerical representation is good for algorithm, and especially for clustering algorithm, which will help us finding similarities and grouping things together, and then we'll spit out the report onto which you can on which you can act. Right. So as you are collecting files, you want to bring them together. And I strongly recommend, if you are not yet using ORHEL, let's have a poll. Who is using out of the box logging that your framework or gives you? Okay, you who uses some kind of structure, so structure logging or even something, more structured. Yeah, perfect. So because when you use structured formats, new boundary grouping, it's easier to do the analysis afterwards because you've got the log entries already, you've got the parser ready. It's easier to make analysis than on contents of the single cluster, for example. If the log stream is too large, and if you are really like producing gigabytes per hour, then for the purpose of this, of getting to know what system is doing, you can sample. So either your log agent or your query can just do like, give me 10% or give me 1% of the log messages. It should be just as representative. So what can you use to collect the logs? So if you are on cloud, probably the easiest way to start is to use whatever your cloud provider is offering. We have quite a good experience with log analytics. We have an experience with CloudWatch logs. FluentBit is an open source tool that allows you to use it as a log collection tool. So, for example, for CloudWatch, we drew out the standard CloudWatch agent AWS is offering, and instead went for FluentBit, so we can customize it the way we need it for later quips. Or if you are building like a full search stack for you, then I recommend using like whatever Vista stack. So if your logs go to Grafana Loki, then you will be using Alloy. If your logs go to OpenSearch, you will probably be using Lofted and PowHeat. Right, so now our logs in a central location. We need to parse it. We don't need much. So there's a sample code. I will share the link at the end for such pipeline. But it is not a universal tool. But anyway, the way I designed it, that tool is the log entry is really small. Just extracting body, extracting exception. The processing pipeline is using parallel string processing. So it starts with the producer. So from your set of log files, it will be producing individual log entries and passing them to a consumer. That consumer will use something. Yeah, if you don't know this syntax, this kind of allows you to create a consumer that can throw any exception without you needing to specify which exception it is. Which is not nice, but yeah, that's probably one of the limitations of the strings that cannot handle checked exceptions well. Okay, so we now have the log entries in our pipeline. Next, we need to turn that into a representation that allows for grouping. And we'll be comparing two approaches here. One is term vectors, which is basically an histogram of number of times a particular term is there, the log message, and embeddings, which is basically a classification algorithm, which also produces a vector. First, I was speaking a lot about term vectors to show like the entire pipeline. Then in the end, we will compare it with the embeddings. So, what is a term? A term is a single meaningful part of a log entry. So you usually just take your message and split it. For example, you can split it at word boundaries. Yeah, that's the simplest possible thing. You just split it into words. You may do some more processing on that. You may throw some of the terms out because they don't help distinguishing the message. For example, if you drop word Java, you probably will not lose much of the information from the message. And then you can use stemming, which means like for every term converting it to the base term. In English, that usually means just dropping the plurals into singular form. In Slavic languages like Polish and Slovak, you can write a PhD thesis on doing stemming. But again, it's not necessary for the log files because the log files are hopefully in English. So there's no need for such transformation with the term vectors. So the vector itself, what is it? It's index sequence of numbers. So we've got lots of numbers where each position in the vector will represent a frequency of a term. So for every possible term on your input, you got one position in that vector, and the number at that position represents the number of times that term is occurring in the log entry. So you will end up with a very sparse vector, including mostly zeros. Because you might have tens of thousands of terms in your entire input, but your log message probably has dozens or hundreds. So the best implementation of a term vector in Java is therefore a map. So we go for every term, we just count the numbers, the amount of times it appears in the log message, and that's our term vector. And for the vector, we implement two methods. One is like a typical operation from linear algebra called dot product, where you multiply together matching positions in the vector. So that's how we do it here. So for every entry of our vector, we just say, we just multiply by the value of the other vector, or if there's nothing there, it's a 0. And the other operation is magnitude, which is normal Euclidean length of the vector in that space in which it resides. So, all right, how do we use that to find whether two log entries are similar? And we will use following trick or approach. So that vector is still a pointer, we can really imagine it's like an arrow somewhere, It is in 10,000 dimensions. So you really need to use your imagination, but you can think of it as that. So anytime you've got two of such vectors, you can compute the angle between them. And since they represent frequencies, what it means is if the angle is small, the words that are present in each message are similar. So there are similar relative frequencies of those words. So, and to compute that angle, we will use exactly the two methods we just mentioned. You take a dot product of the two vectors, divide by the magnitudes, and you get a cosine of the angle that they have together. So intuitively, what this means is when cosine is 1, then the vectors point in exactly the same direction, meaning the relative frequencies are the same. So that happens when one message is multiple of another. So one message says this is a test, and the other message says this is a test, this is a test. Then your cosine is 1. If it is 0, that means that no terms matched. Each one is different because for each term on the one vector, there's nothing on the other. So so one says this is the test, the other one says hello world, if they have nothing in common. Cosine also can be negative, but not for term vectors because term vectors have all components positive. So we need to account for that. So again, we've got 1 is similar, 0 is different. When we are grouping, we want the opposite. We want that things that are close together are close to 0, so the distance is close to 0. And if they are different, we want a number to be positive. So if we take 1 minus this value, this can serve as our distance metrics we will use for clustering or finding similar documents. And we will pick the threshold of how close we want those documents to be, and that's how we get the similar entries. And there are multiple algorithms you could choose from. The best ones, if you define like how exactly you want your cluster to look, what it needs to satisfy, they tend to be NP complete. You need to try all of the options, which obviously you cannot do because with 10,000 log entries, you basically run out of universe waiting for this to complete. So instead, there are different solutions which are quadratic, which is still enough of computing if you need to compare like each message to every other message. But we can compromise. We can compromise because if we don't, we are only looking for really documents that are really close together in a convex way. So if you imagine that vector in the 3D space, you're really looking, you really want to find something that is like within a cone. So if you would have your entries like within this cone of light, they will be similar because they will be within single angle threshold. And we don't know how many clusters you want exactly, but for practical purposes, you want 100 to 200. You'll end up with a report that is still kind of easy to read, and you can get through it in half an hour and know what is happening. So when I first started with that, I wasn't really researching clustering algorithms. I just implemented the first thing that had appeared as a solution for me, and it worked quite well. So that's what I keep using until now. And it is a naive clustering. So for every log message, for every the vector that I'm inspecting, I'll just look in the list of existing clusters. If there's something where this will fit, where this close enough, if yes, I'll put it here, but put it over there. If not, I'll start a new cluster. In Java, it looks like this. So we've got our something that defines our metric. So this 1 minus cosine of the angle, and the threshold for an item being part of the cluster. And as we are adding a new document, we find if there is something close enough. If yes, we add it in cluster. Otherwise, we start a new cluster. And finding the match is then a parallel operation where we compute distance to all of these leading vectors of the existing clusters, sorted by distance if it is within the threshold. That's how die. That's where it lands. Also interesting, Java PKA probably don't know. You can define a report inside of method and use the Java inside that method. So if you want to, if you quickly just need to store a set of numbers or set of objects in a map or here in a stream, that's efficient way of doing that. Okay, so that is the algorithm. So let's look on some results of a clustering, and for that I deduce two data sets. One is our control plane logs, which was around 24,000 entries, ended up doing 200 clusters. Processing time for that with that algorithm was under a second on what was that, an i9 desktop machine, so like 16 cores. And then I wanted to use something else because I know it works for me. Does it work like generally? It is hard to find logs for analysis because people usually don't make logs available for download unless it's it's an information leak in making. But there is this project or this paper called LogHub where they collected some of the logs, and I chose Hadoop dataset, which is under 200,000 entries. And again, it ended up doing like around 162 with same parameters. I got 162 clusters in about 3 seconds. So what does that mean that I got the cluster? This is a really nice chart. What it tries to convey is how large the clusters are compared to the entire size of the data set. So, and at the cloud data set, we ended up with one, the largest cluster, which took about 35% of all the entries. The other one was like 15, 10, and so on. Ultimately, the 9 largest clusters are almost 80%. So, like at this point, it's good to start looking on the chart now. So 80% landed in 11 clustered. The remaining 20% created another 180. So it kind of represents of how logs are composed. You will have lots of repeating messages with small variants. Those will land in those large clusters, and then you might have unique messages, and that there might be hundreds of different kinds of such relatively unique messages or not less frequent messages. Similar thing on the Hadoop dataset. Large cluster make up for almost 60%, and then there's only like 30 clusters also on in the 90th percentile, and only the last 10% will create yet another 100 clusters. So, but that doesn't give you enough information what is happening. It just gives you insight of what might be the structure of those log files. To actually be able to act on it, you need to go with the next step and make a report. Again, this choice of reporting format is up to you. I ended up with a text file that you just scroll through in a text editor. And I suggest that you include like the size of the vector, the time span, so whether that thing happens all the time or was it an isolated incident. Some stats on the similarity is a good show off, but it's really hard to interpret. The most important part are the sample entries. So you want to have 10 to 20 examples of what is there in that log file, so that you can act. And usually you end up doing one of the 4 things. It is either a bug that you recognize from those logs and you go and fix it, or you're not sure and you want to know, does it happen often? Are there some other properties we need to compare for these log files? So you will need to make some analytical pipeline next to that. It will tell you, okay, for this particular cluster, can we just split it out by time of the day or by request path or something like that? So you will want to do further analysis. Or you'll tell, okay, so 10,000 of my log messages are junk. They give no information. I should just drop that log statement or make it go from info to debug or something. Or you want to set up an alert. So next time this happens, I want to know immediately, not in 2 weeks or in a month when I run the report. So let's look on some examples of those. This was the most prevalent message. It's probably hard to read, but what it says, basically, it was in our cloud backend. We've done the refactoring, and this message was telling that this particular subscription is missing some data and you cannot use the new code path, and we need to call back to the old code path. Notice that we are also using like JSON for the body of the message. We do it to enable analysis later. So you call that your log files, but you know that particular logger is again outputting structured content. So you can take that structured content, and it is easier than to quantify later. So for that, we wanted to know like how many different subscriptions use that. So we already know, okay, I'll get that message, I'll parse that to JSON, and then find I can do like this and filter on that. Or the other error message was really an exception that says, I cannot see it by a list was null. So what we did, with those, we fixed them. We added the missing data for those subscriptions. We fixed the goals so it anticipates that the price might not be there. Right, another large part of our data set was basically 404, where we found out that good people of the internet are probing our system, looking for credentials, looking for Git repos. So for that, just knew, okay, we need to be aware of that. We need to know like how often is it is happening. Are those different IP addresses? We'll show you about that. Or we may then later decide to fix and straight blacklist the IP that tells that, or just tie that resources that leave the response dangling for 10 minutes so you don't do anything else in the meantime. But that's up to you. First, you probably need to know how frequent the problem is. Right. Then we've got things like this, where we found out, that is part of every deployment we are performing. And at the end of the deployment, we disconnect from the log, but there's actual messages like deployment finished. So this is pure noise. So we decided to suppress it, to drop at that log entry. And for the final one, we found our database was down for a second because it was actually going a maintenance. Your path provider will not tell you when exactly maintenance starts. So we probably want to be aware. We know nothing bad will happen because the system can't recover from it, or at least we should know. So we could then set up an alert. And we now know the exact structure of the message, so we know what to write there. Right, so this is the byline. So now let's speak about embeddings. So in the process that we showed, we have replaced the term vectors with embedding vectors. And embedding vectors are neural network built from classification. And what it will do, it will parse your characters into tokens. So usually language models have around 5 to 10,000 tokens, by which they kind of classify the sequence of characters, and they take a sequence of tokens and map them to a vector of a fixed size. Usually for the small models, that is like 384. Larger is usually 1,000. Some of them are 2,000, but these two are the most common sizes. And you can use a variety of models. You can have you can use those from AI providers. So you can use them from OpenAI, from Amazon Bedrock, from Azure, whatever that's called, something Copilot surely. Or those models are relatively small. Those are not full language models that will be 30, 60 gigabytes. So you can just run it on your local GPU, even on CPU. Now, if we compare that, the good thing about embeddings is that they have variety per price. So many operations make sense on the vectors, make sense to average to embedding vectors. For term vectors, it is a little bit itchy. And since it is learned classification, they have semantic proximity. So if the message means the same, the vector will probably be close. Those two vectors will be probably close to each other, regardless of what words are actually used. And disadvantage is cost. So it's either slow or expensive, or both. Research intensive means that if you are using a CPU model, what they call, I will show this in a minute. It runs the runtime from 1 second goes to 200 seconds. And so it will either take longer on the same machine. I didn't try using GPUs though, so you may try that. Or it is expensive, but not really expensive. Those the larger data set, those 118 1,000 messages ends up being around 50 million tokens. So that ends up being like 20 or 30 cents. So it's still acceptable, but no, it's more than zero. And you probably will want to run it on more than 200,000 messages. So how do we do embedding classification with Java? You will use LangChain4j, which is a very nice library that gives you API for all relevant things. And they have this interface called dimensional embedding, dimensional variable embedding model, which is a common interface that will be implemented by your local models, by your OpenAI interface, by your Olama endpoints, and so on. So it's really easy to try out different implementations. In this particular example, I'm using eSmoggy2, which is one of the models that are well used on CBU. And the funny thing is with those models, you kind of need to tell them a story. Yeah, so they prescribe how your message should be structured for classification. So specifically, eSmoggy2 says you should put query in front and then some text, and many times you don't want just the raw data, you want to get in some context. So it was a log message and what the particular item said. So it is something again you need to fine tune for your input for the model you are using. So how did I turn up looking? In the end, well, you don't remember the previous chart, so this one will be better. So let's just compare how we look on the cloud data set. It creates larger clusters. But yet the items make sense together. So you'll end up with 100 clusters, yes, less. And those large clusters are a little bit larger. So the report will be easier to read. So it's basically trade-off between computer processing power and your processing power when you need to read through that report. And the perfect example of what they can be used for is this set of messages, which says using omnifaces, running on trifaces, and then I went and analyzed the full cluster I had there, and run just trifaces, omnifaces, and Mohara. But those are not the only messages that say like I'm running the particle library at a version. These three specifically are only JSF libraries. So this is the level of semantic grouping you are getting. So it will probably happen in other cases. It will happen if, your problem is persistence related. It will happen if you got one team who calls a thing an order item and the other team calling a thing an order line. Those messages will be grouped together. So this is another advantage you will get with vector embeddings. So in conclusion, it is a really simple and fun task to perform if you want to know what your system is doing. You probably want to build your own or tune your own for the way your application is looking, your system or your platform is storing the logs and the kind of messages you got. And with algorithm embeddings, you can get nicer results, but at higher processing costs. So this will be in conclusion. If you want to try it more, the QR code points to a GitHub repo that has that sample code that you can use as a starting point. Next steps you could be doing the moment you've got your logs in JSON. For example, my tool will also output the CSV file of the groupings. And as you've seen in this step, you can just then do select basically where entry is a JSON file, nothing is a CSV file, and you can just write a SQL query. So this will allow you then to inspect the individual clusters. I think I didn't try, but may give you a good insight is then trying to classify the frequency or the time patterns. So does that thing happen like twice over the period like that, or it happens every hour or every minute? This is also nice additional information, but it's a little bit of more additional programming to do. And the final thing I will point you to is kind of a really nice visualization tool called Trinity, which was specifically built for visualizing embeddings. And if you like transform your output to a specific JSON format, it will then run a dimension reduction algorithm on it. So it will try to project that 384 dimensions onto 3 dimensions, and you can just scroll around, see individual data points, seeing some other groupings that your natural grouping didn't find. Right, that's it. So I think we can jump to questions, which would be here. How compares the performance? Yeah, like I said, 200 times slower. On a CPU. Might get better results if you use GPU. So instead of doing the light chain for J, instead of choosing that particular model, you would instead use, for example, Olama API and running Olama to run that, or Notebook LM or something like that. Compared to Datadog, haven't used Datadog that much. So I know they have some kind of grouping tool as well, right? So it can do some of that. I cannot tell you how exactly. If you are getting the insights you want from Datadog, that's perfect. But alternatively, that can be an additional tool. Yeah, that can be a tool that will tell you, all right, I probably need to set up alert in Datadog for this particular log entry, which I will otherwise ignore because they might not show in any other metrics. So yeah, nothing by the Datadog. 384 better than 386. Yeah, probably because 386 will not be able to compute those 384 numbers at all. So yes. All right, if there are no more questions, thank you for your time. You can find me here today and maybe also tomorrow, or reach me out at social networks on Duditš. Yeah, wherever you look, I'm there under this handle. Yeah, thanks.